Today, we're breaking down the transformer, the architecture introduced in the 2017 paper, Attention is All You Need. This single paper completely changed the game for sequence modeling, paving the way for the massive language models we have today.
The core idea was, frankly, radical for its time. They proposed building a network using only attention mechanisms. This meant throwing out the recurrent and convolutional layers that had been the absolute standard for language processing for years.
So here's our roadmap. We'll define what the transformer is, then zoom in on its core engine, the attention mechanism. After that, we'll look at the full architecture, break down why this approach is so powerful, and finally, check out the impressive results it delivered.
All right, first up, what exactly is the transformer? At its core, it's a new kind of architecture for what's called sequence transduction.
A sequence transduction model is just a fancy way of saying it converts an input sequence into an output sequence. Think machine translation. A sentence in one language goes in, a sentence in another language comes out. It uses a pretty standard encoder-decoder setup. The encoder reads the input and condenses its meaning into a rich numerical representation. Then the decoder takes that representation and generates the output. Now, this high-level structure wasn't new, but what was happening inside that encoder and decoder, that was the revolution.
So let's get right to that revolutionary part, the attention mechanism. This is the secret sauce of the whole model. The specific function they use is called scaled dot product attention. The best way to think about this is like a super sophisticated search engine. For every single word, we create 3 distinct vectors, a query, a key, and a value. The query, Q, is like asking a question. What other words in this sentence are important to me? The key, K, is like a label on every word, saying here's the kind of information I hold. The value, V, is the actual substance of that word. The attention score is calculated by taking a word's query and matching it against every other word's key. That scaling factor, dividing by the square root of d_k, is absolutely critical. Without it, for long sequences, the dot product scores could get huge, pushing the softmax function into regions where its gradient is almost 0, which would completely stall the learning process. So let's walk through it. Imagine the word is kicking. First, you take the query for kicking and calculate its dot product with the key of every word in the sentence. You'd expect a high score with the word ball, right? That's compatibility. Second, you scale all those scores down to keep them stable. Third, you run them through a softmax function. This turns all those raw scores into nice, clean percentages that all add up to 1. So maybe ball gets a weight of 0.8 and everything else gets a tiny fraction. Finally, you take those weights, multiply them by each word's value vector, and sum it all up. The result? A new vector for kicking that is now deeply informed by the context of ball. Now, you could do this just once, but that's like asking a single person to understand every possible grammatical and semantic relationship in a sentence all at once. It's too much. So, the transformer uses multi-head attention. This is like having a committee of specialists. Instead of one big attention calculation, it runs several smaller ones in parallel. Each head can then learn to focus on a different kind of relationship. One head might track verbs and their subjects, another might track pronouns, and a third might track something else entirely. It lets the model look at the sentence from multiple perspectives at the same time. In the original base model, they used 8 parallel attention heads. And here's the clever part. It doesn't really increase the total computation. Instead of having one head work with big 512-dimension vectors, they have 8 heads each work with smaller 64-dimension vectors. The math works out to be about the same, but the model gets this incredible ability to capture 8 different kinds of contextual information for every word all at once. Okay, so we've got the core building block. Now let's zoom out and see how it fits into the full model architecture. The model has 2 main sections. On the left, a stack of 6 identical encoders. On the right, a stack of 6 identical decoders. An input sentence gets processed by the entire encoder's stack. The final output from the encoders, this rich representation of meaning, is then fed over to every single layer in the decoder stack. The decoder then generates the output word by word in what's called an autoregressive fashion. That just means that after it generates a word, it feeds that word back into itself to help predict the next one. If we look inside each layer, an encoder is pretty simple. It has a multi-head self-attention mechanism and then a simple feed-forward neural network. The decoder layer has those 2 things as well, but it adds a third component right in the middle. This extra part is an attention mechanism that lets the decoder focus on the relevant parts of the input sentence from the encoder. And around each of these sublayers, you'll find residual connections and layer normalization. These are absolutely vital for allowing the network to be trained effectively at this stead. So, why does this self-attention approach completely dominate older methods? It really comes down to some fundamental computational properties.
This table from the paper says it all. Let's look at sequential operations. For a recurrent network, or RNN, that number is O of n, meaning the computation time grows linearly with the length of the sentence. You have to process words one by one. But for self-attention, it's O of 1, constant time. You can do the main computation for all words at once. The second column, maximum path length, is where self-attention really shines. Maximum path length is basically the distance information has to travel between any two words in the sequence. In an RNN, for the first word to influence the last word, its signal has to pass through every single word in between. That long journey makes it incredibly hard to learn long-range connections. But with self-attention, the path length is O of 1. Every word has a direct, one-step connection to every other word. This makes learning those long-distance relationships, which is key to understanding language, trivial by comparison. And that O of 1 for sequential operations, that has massive real-world consequences. Because RNNs are inherently sequential, they can't fully leverage the power of modern GPUs, which are designed for parallel computation. Self-attention, on the other hand, is almost perfectly designed for it. You can process all the words in a sequence at the same time. This leads to dramatically faster training times and made it possible to train much larger models. Okay, the theory is solid, but did it actually work? Let's look at the performance benchmarks.
So after all this clever architectural design, does it actually translate to better performance on real-world tasks?
The results were stunning. On the WMT 2014 English to German translation task, the big transformer model hit a BLEU score of 28.4. Now, BLEU measures translation quality, and a jump of over 2 full points is a huge deal. What's even crazier is that it beat the previous state-of-the-art, which was a complex ensemble of multiple models working together. The transformer did it with a single, cleaner architecture.
And just to visualize that, this wasn't a small, incremental improvement. This was a significant leap forward. The transformer didn't just inch past the old record, it established a completely new state-of-the-art, proving that its architecture was not just different, but fundamentally better. And here's the kicker. It achieved these superior results while being an order of magnitude cheaper to train. The big model trained in just 3.5 days on 8 GPUs. This efficiency is what truly unlocked the future. It wasn't just a better model, it was a more scalable one, proving the real-world power of its parallel attention-only design.
The success of the transformer wasn't just an endpoint. It was the starting gun for a new race. It proved that attention was not just all you need, but that it was a far more powerful and scalable foundation than anyone had previously realized, leaving us to wonder, what are the ultimate limits of models built on this one powerful idea?